All right, so when doing these types of problems, remember the first thing we do want to do is look for the square root principle ones, because they're the easiest to identify just by looking at them. We don't even really need to do any work, because you're looking for something that has x appearing in the equation just the one time. And in this case, looks like equation number 1 is our winner there, because in that case we just have the 1x squared appearing in there. So to solve that, I'm going to use the square root principle. Now, a little side note on that one. Notice if we actually did that, we'd add 27 to both sides. We'd divide both sides by 11. You'd have x squared equals 27 over 11. And then, can we take the square root of that? Yeah. Is it going to be a pretty number? No. Keep that in mind. Because so often when we've been doing square root principle, they have come out to just be nice, pretty little numbers. But it doesn't always happen that way. All right, next up, we need to now look for anything that is factorable, because that means we should use the factoring method. And remember, if it can be factored, do so. I don't want you resorting to quadratic formula for everything, because although it can work for everything, it's more prone to error, because there are so many little moving pieces in it. All right, so I want to look to see which ones can factor, which means I need to think about what AC would equal. So like on this second equation, that would be a negative 90. And so I'm looking to see, are there two numbers that add to negative 13 and multiply to negative 90? Oftentimes when we're looking at this one, people have a tough time finding whether that one works or not, because it seems like there's so many different ways to get negative 90. So another option, when you know that there's going to be one of each here, is figure out what that last one would be. Here AC equals 28. It's probably a little bit easier to figure out if there's two ways or two numbers that will add to negative 12 and multiply to 28. Smaller numbers. So you might find that to be an easier one. So let's focus there first then, since we're having trouble with the last one. So to get 28, of course we can do 1 times 28. Are we going to be able to make a 12 out of those two? No. Okay, what about 2 times 14? Can we make a 12 out of those two? Well, you can make a 12 out of 2 and 14, yeah. Like if one's positive, one's negative, we'll get either 12 or negative 12. So that's promising. Great. Now let's just figure out our signs. I need to multiply to a positive 28. Now if I'm going to multiply to a positive, that means both signs are the same. So either both positive or both negative. If we're going to add to a negative 12, that means they would both have to be negative. All right, so negative 2 plus negative 14. Is that negative 12? No, it's negative 16. It's not negative 12. Can I make it be a negative 12? Well, the only way to get a negative 12 is by making the 2 positive and the 14 negative. Will that multiply to a positive 28? No. And so it looks really, really close there, but it doesn't work. So, sorry, that's not a winner either. 3, I'm not going to check continuing my list here. 3 does not go into 28. 4 does. 4 times 7, of course, is where we got it from. Can I make 12 out of 4 and 7? No. Nope. And I've just exhausted all the different ways to get 28. So by doing that, we just showed it cannot factor, therefore we have to use quadratic formula. So going back to that second equation, adding to negative 13, multiplying to negative 90, yes, there is actually a way. Some of you would come up with it. Negative 18. Oops. Negative 18 and positive 5 would give us that. So that's why that one does, yes, indeed, factor. And so we would want to use the factoring method for it. Now it's possible that you would think that you had tried everything and you would think, no, it doesn't factor, and you'd start using quadratic formula. What is that going to look like if it turns out that it was factorable? And can you still use quadratic formula in that case? Well, as an example of that, if you did use quadratic formula with something that was factorable, you'd be doing the work and you'd have the square root part, of course, of quadratic formula, and inside of it you get some number. You go to take the square root of that number on your calculator, and it's going to give you a whole number. If it was factorable and you still try to force quadratic formula into it, you can do it, but the square root's going to give you just a whole number, and that's going to be that little flag to you telling you, okay, yeah, you can keep going with this, but just so you know, it was factorable, so be aware for next time. Because it'll still work. You can still do the math with whatever that whole number is. You just have to be really careful, as you've seen when doing quadratic formula calculations. But that does get us into an interesting topic here, which I just want to at least touch on, which is what kind of numbers can you get out for these? Because like we were taking a look at the start there, when we did square root principle, I was pointing out that that answer that we were just looking at, if we had actually solved that, we would have gotten an irrational solution for that. An irrational solution, remember, an irrational number is a decimal that goes on forever and never repeats itself. All of these square roots that give us funny numbers, basically any square root that's not a whole number, it's irrational. It's this decimal that goes on forever. It's just messy and nasty. So those can happen. Of course, square root principle is typically, though, given us integer solutions. Remember, an integer has no decimals or fraction in it. They're like whole numbers, but they can also be negative. Rational. You get what I mean by a rational solution or a rational number? Rational numbers can be written as fractions. So like, for instance, if your answer was 2/5, that's a rational solution. Can you get answers by using the square root principle that are fractions?
No, you will have to use the formula.
Actually, you can. We actually saw one on last week's WAMAP, when you were working on last Friday, where it ended up looking like this, where we had x squared equals, it depended on what your particular numbers were, but maybe something like that, x squared equals 4/25. And you take the square root of a fraction, you take the square root of the top and the square root of the bottom. And so in that case, x would equal plus or minus 2/5. So yes, it can actually give us a rational solution as well, just a plain old fraction. So square root principle, although it tends to give us integer solutions, that's mostly just because of the types of problems your math teacher creates. It can give you anything. Factoring. What can factoring give us? Well, factoring, of course, we've seen many examples. In fact, I'll throw an example up here. What if it factored down to be x minus 3 times 5x plus 1? If you're solving something that factored out to look like that, notice the first solution here would be 3. That's an integer. But the second solution, if you set that equal to 0, that would be negative 1/5. That would be rational. So factoring can give us rational or integer solutions, but what it won't give us is an irrational solution. You're never going to get from factoring some really messy, nasty square root, because doing so would mean that we actually would have to have seen that that number multiplies by something else and adds to the middle number, and yeah, we aren't going to see that with an irrational number in there. If it doesn't factor, we resort to quadratic formula. Now, technically speaking, quadratic formula can be used to solve any quadratic. You actually could skip knowing anything else about quadratics and just use quadratic formula. The problem is that you're going to make a lot of mistakes along the way, and we don't want that. And so we don't use quadratic formula if it's going to work out nicely. We don't use it for integer solutions, and we don't use it for rational solutions, or at least not on purpose. While it can give either of those in theory, I hope that it will only give you irrational solutions, because we should only be using it as a last resort. So go quadratic formula just after you've eliminated the others. So technically, yes, it can give the other two possibilities, but really, it should be irrational every time if you're nailing all the little details. All right, one last thing to do as a class today, and that is one problem to solve. Please write down and solve this quadratic. Now, of course, the first thing you need to do is deciding which method to use. Hopefully, if you're really on your toes, you might have noticed that you actually already saw and made that decision for this particular equation, because this was the third equation on that very first page we did, where we decided that we should solve this one, since it's not factorable, by quadratic formula. So if you weren't sure where to start, that's where to start, using quadratic formula here. So when you first plug into the quadratic formula, this is what you should be looking at. And then it's just a matter of paying attention to the work and the details along the way, especially the signs. Because if any mistakes are coming up, it tends to be sign errors from here. Right, so you work it all the way through, and at some point in your work you should hit this line. X equals 12 plus or minus the square root of 32 over 8. Now, this is pretty good, but it's not quite done. Because basically this is exact form, which is one of the things we're looking for, but you'll notice that we actually want our answer in simplified exact form. And this square root of 32, it does simplify down. So we actually want to do that work. So the square root of 32, remember you can either break it up with the factor tree into its prime factors and circle pairs, or look for the biggest perfect square that goes into it. Now for me, I look at 32 and I know pretty quickly what the biggest perfect square is because I've done a lot of these. Done a lot of practice with them. So it becomes the square root of 16 times the square root of 2, because 16 is the biggest perfect square that multiplies into it as a whole number of times. So in other words, if I take 32 and divide it by 16, I get a whole number here. That's what I'm looking for. And so I look for a perfect square because the square root of 16 is 4. And so that root 32 is going to become 4 root 2. Now once I've done that, I can now look to see if I can simplify it further. I could not reduce that fraction at all based on the way it looked, because this 32 was trapped inside of the square root and the other numbers were outside of square roots. I can't have those talk to each other. But now that I've done this simplifying, the numbers that were outside of the square root are now joined by the 4, which is also outside the square root. So I look at those three numbers. Basically, I'm looking at all three terms, 2 in the top and 1 term in the bottom. And I'm saying, what can I divide all three of those numbers by? And yeah, you can divide them all by 2, but I can do better than that. 4. So we're going to divide them all by 4. Which gives me then a final answer, and yes, this is our final answer, of 3 plus or minus just the square root of 2 over 2. Now, you're going to be doing some work on these kinds of problems on WAMAP. When you do, if you get this kind of an answer, and sometimes you will enter it in by first doing the 3 plus the square root of 2 over 2. Then you go comma, 3 minus the square root of 2 over 2. And as you type this sort of thing into WAMAP, pay very close attention to the parentheses. You put a comma between them, all that kind of stuff. Or make your life easier, just click on that little yellow arrow that pops up on your text box, and then that makes it easy to just type it in that way too.